Have you ever wondered why your watch ticks slower when you're on a speeding train than when you're sitting still? Well, it's not because of a mechanical fault or a trick of the mind. It's because time itself is not absolute. It changes depending on how fast you're moving and where you are in the universe. This might sound like science fiction, but it's real science. This is the concept of time relativity. The idea that time is not a fixed entity, but a variable that can be stretched and squeezed. It's one of the most mind-bending yet fundamental aspects of our universe. It tells us that time and space are intertwined, that the ticking of your watch can be influenced by the speed of your train or the pull of a distant star. This fascinating concept, known as time relativity, forms a cornerstone of Einstein's theory of relativity. At the heart of relativity lies a simple yet profound principle. It's a concept that forms the foundation of our understanding of the universe. It's the principle of relativity. This principle asserts that the laws of physics are identical for all observers in uniform motion. To put it simply, if you're cruising along at a constant speed in a straight line, there's no experiment you can conduct to determine whether you're actually moving or standing still. You might feel stationary, but in relation to another object, you could be moving, or vice versa. The remarkable part is that the laws of physics work the same way in both situations. They don't care if you're speeding along a highway or lounging on your couch. So whether you're stationary or moving at a constant speed, the laws of physics remain the same. Now, imagine a beam of light traveling in a vacuum. This light, according to Einstein's theory of relativity, moves at a constant speed. It doesn't matter if you're stationary or racing alongside it at top speed in a starship. The speed of light remains the same. It's a universal constant, clocking in at roughly 186,000 miles per second. This idea of constancy is a cornerstone of our understanding of the universe. But what does this mean for us? Well, it's a bit like running on a treadmill. No matter how fast you sprint, the scenery doesn't change. In the universe's grand cosmic treadmill, the scenery is light, and we're all just trying to keep up. But here's the catch. No matter how fast you go, you can never catch up to a beam of light. It's always one step ahead, forever beyond our reach. What if I told you that time can stretch and space can shrink? This isn't just a twist in a science fiction plot, but an actual principle rooted in Einstein's theory of relativity. Let's dive into these mind-bending concepts: time dilation and length contraction. Imagine you're on a spaceship hurtling through space at close to the speed of light. According to Einstein's theory, your clock aboard the ship would tick slower than a clock back on Earth. This is time dilation, the idea that time runs slower for an object in motion compared to one at rest. It's not that your spaceship's clock is faulty. It's just how the universe works. As you approach the speed of light, time itself seems to stretch out, to dilate. Now let's add another twist. From the perspective of someone on Earth, your spaceship would also appear shorter than it actually is. This is length contraction, the notion that an object in motion contracts or shortens in the direction of its movement. It's as if space itself shrinks in response to motion. Both these phenomena, time dilation and length contraction, are significant only at speeds close to the speed of light. At everyday speeds, these effects are so minuscule that we don't notice them. But for particles zipping around in a particle accelerator at near light speeds, or for light itself, these effects are very real. These concepts might seem strange, even counterintuitive, but they are fundamental aspects of our universe predicted by Einstein's theory of relativity and confirmed by countless experiments. They remind us that our intuitive understanding of time and space based on our everyday experiences can be misleading when we venture into realms where the speeds are close to the speed of light. So, the faster you move, the slower your time ticks and the shorter you become. Welcome to the weird and wonderful world of relativity. Let's delve deeper into the relativity realm and explore its other intriguing aspects. The first stop on our journey is E=mc², an equation that even those not immersed in physics might recognize. This is Einstein's theory of the equivalence of mass and energy. It tells us that mass and energy are interchangeable. They are different forms of the same thing. If we could convert an object's mass entirely into energy, the amount of energy we would get is the mass of the object multiplied by the speed of light squared. An incredible thought, isn't it? But Einstein didn't stop there. He went on to propose the general theory of relativity, an extension of his earlier work. This revolutionary theory describes gravity not as a force, as Sir Isaac Newton did, but as a curvature in space-time caused by mass and energy. Imagine space-time as a fabric. A massive object like a planet or a star would sit on this fabric, causing it to curve or warp around the object. Smaller objects moving in the vicinity of this massive object would then move along these curves. This is what we perceive as gravity. It's as if the massive object has choreographed the movement of the smaller objects around it. Einstein's theories radically changed our understanding of the fundamental laws of the universe. They proposed a universe where space and time are woven together into a four-dimensional fabric, where mass and energy are interchangeable, and where gravity is the result of the warping of space-time. His theories have been tested and confirmed time and time again, leaving an indelible mark on the world of physics. So, in the grand dance of the cosmos, mass and energy are interchangeable, and gravity is simply the choreography of space-time. To sum it all up, Einstein's theory of relativity challenges our common-sense understanding of time. From the constancy of light speed to time dilation and length contraction, it all points to one reality: time is relative, not absolute. The profound equivalence of mass and energy, along with the curvature of space-time, adds to this fascinating complexity. So next time you glance at your watch, remember, time is not ticking away at the same rate for everyone, everywhere. It's all relative.